Japan's mighty Akashi Kaikyo Bridge, the highest, longest, most expensive suspension bridge on the planet. It stands here against all odds and is built in a place no bridge should be, Typhoon Alley, at the mercy of winds that reach a staggering 290 kilometers an hour. That's powerful enough to tear roofs off houses and uproot trees. It crosses one of the world's busiest, most dangerous shipping lanes. Even worse, it's smack in the middle of a major earthquake zone. It's a bridge they said could never be built. The colossal Akashi Bridge carries a huge 6-lane freeway, linking the bustling metropolis of Kobe on the mainland with the island of Awaji to the south. For the people of the fishing villages on the rural South Island, it's a vital link to hospitals, schools, and the city on the mainland. For Japan, it's a symbol of national pride, the final link in a network of bridges that will unite all 4 islands. It's a vast feat of engineering and holds no less than 3 world records. At 280 meters, it's the highest suspension bridge on Earth. Its 2 towers each stand as tall as an 80-story building. With a central span just over a mile, it's the longest suspension bridge in the world, nearly twice the length of San Francisco's Golden Gate. And at $4.3 billion, it's the most expensive bridge ever built. The water it crosses is a bridge builder's nightmare. The Akashi Strait is a 4-kilometer barrier of hostile sea that divides the island of Awaji from mainland Japan. Over 100 meters deep, with currents that rip through at 14 kilometers an hour. That's on a good day. Typhoons regularly tear through the area, whipping up winds to a terrifying 290 kilometers per hour, destroying almost everything in their path. The strait is also one of Japan's busiest shipping lanes, the main artery that links all 4 islands. Every day, over 1,000 ships plow through these densely crowded waters. Each spring brings even more dangers. Dense fog engulfs the channel. Hundreds of ships perish here every year. For decades, the local and national government talked about building a bridge across the barrier of the Akashi Straits. Before the bridge existed, the only way to cross this sea was by ferry. With boats crisscrossing the crowded strait, it was only a matter of time before disaster would strike. 11th of May, 1955. 100 school children boarded the Shionmaru ferry for the 45-minute crossing of the strait. The ferry had to pick its way through the busy shipping lanes in thick fog. 15 minutes into the crossing, an incoming ferry appeared out of the mist. There was no time to change course. The Shionmaru ferry took just 5 minutes to sink. 168 children and adults were drowned. The tragedy sent shockwaves through the community. Demands grew for a bridge to be built to stop a tragedy like this happening again. Engineer Makoto Kitagawa is executive director of the Honshu Shikoku Bridge Authority and worked on the early designs of the bridge.
This accident might probably the start for the government to think of the necessity of the bridge project.
To deal with the awesome challenge, the Japanese government set up the Honshu Shikoku Bridge Authority. It had the task of building the impossible. It took 30 years of research into new technologies before building could start. May 1988. When construction began, engineers were faced with the most daunting task of their careers. Ahead of them lay 10 arduous years of unknown challenges, setbacks and disasters. Building the world's biggest suspension bridge was a monumental undertaking. Over 2 million workers, billions of dollars, and 181,000 tons of steel and 1.4 million cubic meters of concrete. Its foundations are the size of 20-story apartment blocks. Its towers almost as tall as the Eiffel Tower in Paris. And enough cabling to circle the globe 7 times. As one of the world's leading bridge builders and one of the only foreigners to work on the project, Jim Cooper knows the enormous difficulties the Japanese faced.
It is a huge mega project undertaking, pushing technology to the limits.
In theory, suspension bridge design is simple. 2 main cables stretch across the water, held up by 2 towers. The roadway is hung from these cables, and it's all anchored down on each side. It's a tried and tested formula, and it works. But there is a limit to how big a suspension bridge can be. This is the size of the Golden Gate, but the Akashi is going to be nearly twice the size. To stop itself from collapsing, the cable and roadway will have to be much stronger and as light as possible.
The longer a bridge gets, the more weight is involved. A suspension bridge must be designed first and foremost to carry its own weight, and then the remaining strength of the bridge is able to support the traffic load. The Akashi Bridge supports 91% of its own weight, with only 9% of the total load being carried for vehicular traffic by the bridge itself.
May 1988. The first problem the Japanese faced was where to site the enormous foundations on which the whole bridge would sit. And already the treacherous Akashi Straits caused a mega headache. The ideal place was right in the middle of the busy shipping channel. But this made them a major hazard for the countless ships that steam through these waters every day. To safely avoid it, the bridge's foundations had to stand nearly 2 kilometers apart. And it's this span that makes the Akashi the longest suspension bridge in the world. But there was another, even bigger problem to solve. Normally, bridge foundations are laid out in the middle of the water. Cylindrical sections are filled with concrete and sink under their own weight. The process is repeated, building up the foundations from the riverbed in stages. But the Akashi Straits are 110 meters deep, far deeper than most bridge foundations are normally built in. What is more, the fast currents mean normal building methods wouldn't work as they would be swept away. So the bridge designers came up with a solution. It was new, untried on this scale, and risky. They proposed building 2 enormous steel molds on dry land, one for each of the bridge's 2 foundations. Once built, they would be towed out to sea and sunk with pinpoint accuracy.
Nothing on the scale of magnitude has been attempted before.
March 1989. 1 year since work began on the bridge. The giant steel molds for the bridge's foundations are completed in dry docks beside the straits. The hollow double-skinned steel rings stand 70 meters tall and 80 meters wide. They're ready to be towed out to sea. It's a nerve-wracking time for the engineers. Nothing else can start until the foundations are correctly in place. But it's a big gamble. One mistake and the foundation could be swept away. The engineers would have to start again, and the whole year's work would be wasted. March 1989. Work on the longest suspension bridge in the world had reached a critical stage. The 2 giant molds for the foundations were about to be towed into position, and there was no margin for error. The engineers needed the perfect tide and current. One mistake, and the giant hollow molds could have been swept away in the turbulent sea. the whole project could be in trouble. 5:30 p.m. on the 26th of March. 12 tugboats set out from the docks, hauling the first of the massive hollow structures into the racing seas. It's no easy task. Each mold weighs 15,000 tons, the equivalent of 40 jumbo jets. With coast guards keeping lookout, the tugs pull the immense floating skyscrapers through the busy shipping lanes across turbulent seas. It's highly dangerous work. Nobody needs another shipping disaster. It took 38 hours to get each of the two huge molds into position. Now the Japanese faced their first crucial test. For weeks before, they had excavated the seabed to create a perfectly level site. They have to sink two monster steel rings 60 meters into the ocean to support the huge suspension bridge. It meant filling each one with water until they fell to the seabed. They needed to land precisely, otherwise they wouldn't be level and the entire job would be in jeopardy. But they were battling against the worst possible conditions. The tugboats fought powerful currents to hold the hollow rings exactly in place as they sunk to the bottom. 32 pumps poured thousands of gallons of seawater into the outer walls of each of the gigantic molds. Each one was filled with over 250 million liters of water. Slowly, very slowly, they began to sink. Engineers had to wait an agonizing 8 long hours for the foundations to settle on the seabed. But they still didn't know if the mission was a success. Anxious engineers did their calculations to see if they had landed perfectly in position. Miraculously, they showed the huge steel cylinders were resting only 10 centimeters, less than a pencil length from their designated spot, and perfectly level. The extraordinary plan had paid off. But there was still a long way to go. To complete the massive foundations, they had to be filled with concrete. But there was a problem. The foundations are filled with water. If you pour ordinary concrete into water, it disintegrates like a soluble aspirin. To solve this problem, the Japanese had to do something that had never been done before. Create a super concrete that would actually harden in the water.
So the Japanese had to come up with a special formulation for the mixture design of the concrete.
The new concrete would replace the seawater, holding the foundations down. The massive operation began. The foundations were filled with 265,000 cubic meters of concrete. New super concrete and the feat of building foundations in the middle of the sea was a proud moment for Makoto Kitagawa.
The technologies of offshore construction pushed the boundary of the civil engineering.
It had taken 4 years to get to this stage, and only now did the serious building work begin. July 1989. Work started on the two giant 80-story towers that would support the vast cables that carry the full weight of the bridge. Each one would be almost as tall as the Eiffel Tower. But they didn't just have to carry the enormous cables. They also had to withstand one of nature's most terrifying forces. Japan lies smack in the middle of a major earthquake zone. The country straddles 4 tectonic plates that cause havoc when they collide. Japan gets hit by a big one almost every decade. The most destructive one was in 1923. It registered 8.3 on the Richter scale and destroyed Tokyo. Up to 100,000 people died and 40,000 others were reported missing. 70 years later, the bridge builders were acutely aware another catastrophe was due any time. In the bridge's projected 200-year lifetime, it will have to face big quakes regularly. The engineers also knew that concrete towers could crack and crumble in an earthquake because they aren't flexible enough. Their plan was to build Akashi towers out of steel, a material they believe would withstand the shock of 8.5 on the Richter scale. Each tower was made up of 90 160-ton sections, stacked one on top of the other like giant building blocks. And each section had to be perfectly flat. Any irregularity would be amplified as the towers stacked higher. If either tower is off by more than a thumb's width, when they reach the top, the whole bridge will collapse.
The towers are actually built block by block, rising some 300 meters above the sea. Erection of the towers required absolute precision construction, and precision accuracy was absolutely paramount in that only some 2.5 centimeters of offset from the vertical was allowed.
The Japanese engineers are perfectionists, and they had a huge amount at stake, their reputation and $4 billion. They polished the surface of each monster steel block to a fraction of a millimeter. All the joints had to be perfect, or there was no point building the towers at all. Then came the moment of truth. The huge steel blocks that made up the towers took to the seas to be piled high on the concrete foundations. Massive floating cranes hauled these 160-ton blocks across tempestuous seas. It took 90 of these blocks to build each tower. The task was a dangerous one. Once they reached the middle of the water, the operator of the climbing cranes hoisted the massive 160-ton blocks into place. Once each one was fixed in position, the crane then hauled itself up to the next level and started again. Each tower is held together by 700,000 bolts. It took 18 months for the towers to reach their full height of 283 meters.
The design and construction of the Akashi Bridge is really quite unique. Just the sheer magnitude of the size of the bridge is really quite daunting itself.
With the final block in place, Japanese engineers nervously checked the tower's alignment. Incredibly, they were within a thumb's length of being perfectly vertical. It was an extraordinary feat of engineering. The Japanese were jubilant. Stage 2 was completed. The two 283-meter steel towers are strong enough to support the massive cables and roadway, and flexible enough to withstand extreme conditions of typhoon winds and earthquakes, elements most feared in this part of the world. But how do you test this? Simple. You send dozens of men to sway on the top of the towers. Incredibly, the towers are designed to move from side to side. It's this flexibility that helps the finished bridge to withstand the elements. But the only real test would be when disaster struck. Half-built, and the $4.3 billion bridge was at its most vulnerable. The structure only attains its full strength when the cables and roadway are in place. Speed was vital. An earthquake could spell disaster. It was a race against time and the elements to complete the bridge. In November 1993, the engineers began the project's most critical task, building the huge main cable, over 1 meter thick, that would carry almost the entire weight of the bridge, all 160,000 tons of it, 3 times the weight of the Titanic.
The main suspension cables are the heart and soul of the load carrying for the bridge itself, as well as the vehicles and traveling public.
300,000 kilometers of cable is needed, enough to circle the Earth more than 7 times. Each of the 2 main cables is made of 37,000 strands of wire. The weight of such a massive cable is one of the elements that limits the length of the suspension bridge. The longer it is, the heavier it becomes, until the bridge collapses under its own weight. To span the 2-kilometer stretch between the towers, the Japanese had to develop a steel wire twice as strong as conventional wire. It would make it possible to use only 1 cable per side instead of 2. First, the Japanese devised new underwater hardening concrete. Now they created a new super strong steel wire.
It was the first time to use such high tensile cable wires in the world.
This super strength wire is only made in Japan. They changed the composition of the steel, adding alloys and silicon, and created a wire of world-beating strength. One 5mm strand can support 3 family cars. It takes 37,000 of them to hold up the bridge. Making the main cables was yet another mega first. It had never been done on such an enormous scale before. First, 127 5mm wires were pulled together into strands. Each cable was made up of 290 of these strands, 37,000 wires in all. The finished cable is over 4 kilometers long. But building the cable was not their biggest challenge. Now the Japanese had to string the vast cable over the towers and across the busy shipping channel, more than a 4-kilometer wide gap. Before this, they had to get the guide rope over the Akashi Strait. Only then could they begin pulling the strands of the cable across. But the bridge builders couldn't close the busy shipping lane. They were forced to take a far more dangerous route, in the air. 10th of November, 1993. A still morning, just a light wind. Conditions are perfect. A helicopter prepares to take to the air with a super strong Kevlar rope and guide it across the top of the towers. It's like threading a needle with a chopper. It's going to need a highly skilled pilot to do the job. It's a high-precision mission. There's no room for maneuver. The pilot must thread the rope nearly 2 kilometers across from tower to tower, high over hostile waters of the Akashi Straits. "8:03 in the morning. The helicopter lifts off on the Kobe side of the strait. As it climbs to 290 meters, everyone is keeping watch. On top of the first tower, bridge engineers wait to catch the rope. It's a big responsibility for the pilot and a potentially dangerous job. Once it's caught, the pilot has to hover while they anchor it down. It takes 10 agonizing minutes to attach it to the top of the first tower. Now comes the 2-kilometer flight across the open strait, threading out the cable behind him. It It takes 27 minutes to reach the second tower, where a team of engineers wait ready to catch the cable. Fortunately, the cable is again anchored without a hitch. After 84 minutes of tense flying, the helicopter lands safely. It's been a phenomenal feat of flying skill that's needed nerves of steel. To everyone's relief, the mission has been a resounding success. So that's the guide rope across. Only the 37,000 more wires of the main cable to go. December 1993. For the people of Kobe and Awaji, their dream bridge was slowly taking shape. Massive foundations had been sunk 60 meters down to the seabed. On top of these, two huge 283-meter towers stood proud in the middle of the Akashi Straits. The Japanese engineers now faced the daunting task of building the cables up and over these towers. This job started with just a single slender guide rope. It's along this that all the catwalks and cables would be hauled until the 1-meter thick main cables are completed. Catwalks were now built along the pilot rope 280 meters in the air. This mesh was all that stood between the workers and the unforgiving Akashi Straits below. There was no time for vertigo. Workers needed to have a head for heights as they pulled the bundles of cable across. Each bundle was made up of 127 wires, and the workers were going to have to pull an astounding 290 of these over the towers. It took 5 months to build up the bundles to make the 1-meter diameter main cable. The bundles were finally squeezed together, wrapped in a rubber coating and painted to stop corrosion. The cable is designed to withstand the worst of the elements for the next 200 years. On each side of the strait, the giant cables were anchored into 350,000-ton concrete blocks. December 1994. After 6.5 years of toil and trouble, the world's biggest suspension bridge stood half-built in the middle of the Akashi Straits. Now the Japanese had to construct the roadway to carry the 6-lane highway 4 kilometers across the straits. This was the most critical and complex part of the project, and it's the most at risk from the unpredictable forces of nature. The road deck is literally suspended from cables and held down by its own weight. Get the design wrong, and strong winds can flip this platform like a child's toy, with truly cataclysmic results. For suspension bridge designers, wind is the greatest enemy of all, the nightmare scenario. Throughout history, rogue winds have taken engineers by surprise, with disastrous consequences. The most infamous incident happened in America, at Tacoma Bridge in 1940. Harold Bosch of the Federal Highways Association is an engineer who specializes in bridge aerodynamics.
The bridge was opened to traffic July 1st, 1940, and it collapsed on November 7th, same year.
Almost every day of its short life, the bridge moved in the wind with a vertical heaving motion.
These weren't necessarily alarming. They were a regular occurrence, and they seemed to be fairly steady and controlled.
Nothing that could be called a high wind ever hit the bridge, but it kept oscillating, and this was about to become a problem. November the 7th, 9:40 a.m. Wind speed is 68 kilometers an hour and continuous. The bridge begins to move vertically.
In late morning, it switched into a torsional motion and started twisting in the wind.
The wind had hit the bridge at a critical speed, causing it to vibrate. Even though the wind stayed constant, the movement was exaggerated. This is known as flutter, and it's catastrophic. 11:10 a.m. 2 hours after the wind first hit the bridge, the structure begins to fracture. The bridge shatters into pieces.
The collapse of Tacoma seemed to be a milestone because it brought to the forefront the fact that engineers need to take very seriously how sensitive large structures, especially bridges, can be taken down with such low wind speeds.
In Japan, the designers of the Akashi Kaikyo Bridge won't let it suffer the same fate. This is one of the largest wind tunnels in the world, built to test a massive 40-meter scale model. The Akashi Bridge is twice the size of Tacoma, and it will have to withstand winds far mightier than those that destroyed the Tacoma Bridge.
One of the most difficult issues in suspension bridge design, typically because of the location, are typhoons or hurricanes, tornadoes, high wind speeds.
For 3 years, designers struggled to find the perfect aerodynamic shape. Because of its colossal size, the deck needed to be strong enough to support its own weight and the traffic traveling on it. But it also needed to be slender, so wind can pass through it. The designers knew their structure will have to withstand some of the strongest winds on Earth. The Akashi Straits sit right in the middle of Japan's Typhoon Alley.
Typhoons are monster storms, like the hurricanes that devastate the eastern seaboard of North America.
A typhoon's swirling winds can hit 290 kilometers an hour, strong enough to overturn cars, uproot trees, and destroy everything in its path, including buildings. Memories of Typhoon Nancy that wreaked havoc in the region in 1961 still lingered in the minds of Japanese people. Nancy killed 202 people and destroyed over 15,000 houses and left 70,000 people homeless. The designers knew it was only a question of time before the Akashi Bridge would face such deadly force. To beat the power of the wind, engineers came up with an incredible concept. The deck is made up of thousands of steel girders. They're laid in a triangular grid, one of the strongest shapes in the engineer's toolbox. For extra strength, they added a vertical stabilizer that runs down the center of the bridge. It looks like the tail fin of an aeroplane and hangs beneath the deck. When the wind blows, the stabilizer balances the pressure above and below the roadway and reduces the kind of vibrations that destroyed Tacoma. They also installed steel mesh grating down the center of the road and along the sides. This allows the wind to pass right through the roadway and stops pressure building up underneath it. January 1995. 7 years after the huge project began, the final phase of the world's biggest bridge was about to start, the building of the roadway. Until this was finished, the whole structure was highly vulnerable. Bridge builders call this stage temporary condition. It's the most dangerous time for the bridge, particularly in a land prone to earthquakes. Almost all collapses happen during construction. The Japanese were keen to get the deck in place and finish the project, but things were about to go disastrously wrong. January the 17th, 5:46 in the morning. An earthquake rocks the city of Kobe. It's the biggest earthquake in Japan since 1923 and measures a hugely destructive 7.2 on the Richter scale. It destroyed the city. Kobe, most people were asleep. Norikazu Kato, who worked at the Osaka Bay Traffic Advisory Center, was at home as the earthquake hit.
It was still pitch black when it happened, and my family and I were at home asleep. I think it was about 5:45 in the morning. There was a terrible shaking sound.
The earthquake is one of the worst to hit Japan in living memory. In a matter of minutes, 100,000 buildings collapse. 40,000 people are injured. Over 6,000 are dead.
I was shocked to hear that so many people were killed. Many houses and many buildings and many bridges were damaged or destroyed.
It twists highways, topples expressways, and cracks railway tracks.
After the earthquake happened, all the furniture was scattered around, and everything was smashed and broken. When I went outside and looked around, I remember seeing black smoke rising from Kobe.
At first, the devastation was so great that no one thought of the bridge. People in Kobe were struggling to save their lives and belongings amongst the rubble. The epicenter was 20 kilometers from Kobe and only 4 kilometers from the Akashi Bridge. With the roadway still unfinished, the structure was acutely vulnerable. 435 kilometers away in Tokyo, one of the bridge designers, Hirokazu Ohashi, watched news coverage of the devastation with horror.
We knew that the bridge is under construction, the tower is built, and the cable was spanned, but we're not really sure what condition the bridge is in.
Back at the bridge, engineers were relieved to find the huge structure was still in one piece. Initial inspections revealed no damage. The foundations, towers and cables were still standing. However, a few days later, they did a more detailed survey. Launching an underwater remote vehicle, an ROV, to inspect the bridge's foundations. At first, pictures from the ROV of the seabed suggested everything was okay. Then the remote cameras revealed the extent of the disaster. Engineers were horrified. There was a fault line in the Earth's surface right between the bridge's 2 towers. Makoto Kitagawa was one of the first to hear the news.
In 2 days after the earthquake, another report came to us from the construction office. It was quite incredible, and it shows that straight line connecting 4 foundations was not straight.
The survey results were extremely alarming. The anchorage and tower on the Awaji Island side had moved sideways by over a meter. Just as worrying, the earthquake had stretched the length of the bridge by a full meter. It was a real blow for the designers of the bridge. Engineers began to worry about what this would mean for their building schedule.
I felt at that time that there might be a large delay in the construction.
But the bridge engineers were extremely lucky. Ironically, despite their worst fears, their bridge was still standing because it was only partially built. Had the roadway been attached, it could have suffered severely. The towers had survived partly because of their flexible steel construction, but also because of their special earthquake-proof design feature. Inside each of the 2 massive steel towers are 20 huge shock absorbers to help the towers stand firm against wind and earthquake. These giant pendulums can swing in any direction. If an earthquake pushes the bridge one way, the pendulums move the other. It's the only bridge in the world to survive such a massive vertical shock during construction. February 1995. A month after the earthquake, the engineers were keen to start construction again. But big questions need urgent answers. How could they lengthen the bridge by a meter when they had spent years designing the bridge to the nearest millimeter? It was a huge extra amount. For the bridge and its team, it meant back to the drawing board. 30 years of painstaking research and testing hung in the balance. Engineers couldn't just add a meter. The extra length would affect more than just the deck.
We had to accommodate the changes of the profiles and the bridge foundation's locations by changing the design itself.
In the design office at the Honshu Shikoku Bridge Authority, the team struggled to rescue the vast project. There was only one way forward. The huge fault in the ocean floor had pushed the two colossal towers over 3 feet further apart, raising the height of the two massive suspension cables that hang between them. But to their relief, the calculations revealed that they needed to do two things. First, they had to slightly space out the hanger cables that connect the two massive main cables to the deck. By doing this, they could then lengthen the bridge girders that made up the roadway.
It was decided to change the length of the girder, so redesign were carried out by the contractors in a hurry.
Now the Japanese had to put their calculations into practice. They had to build the extended bridge. The longest bridge in the world was about to get longer. After 7 years of Herculean effort, work on the world's longest suspension bridge came to an abrupt halt following a massive earthquake. Engineers had worked overtime redesigning the bridge to find out if they could make it longer. Finally, they had the solution. The answer was to extend the deck by about a meter. At the same time, they had to lengthen the distance between the hanger cables that will hold up the deck by the same amount. Incredibly, construction had only been held up by a month. June 1995. The final decisive stage of the Akashi Kaikyo Bridge began. Massive 100-ton steel sections of the roadway, each bigger than a tennis court, were carried out to sea by some of the world's biggest floating cranes, specially built for the job and capable of lifting 4,000 tons. It took 15 months for the 290 girder sections of the roadway to be assembled bit by bit across the strait. On the 18th of September 1996, the last section is bolted into place. Of April 1998. The bridge opened for business with a huge ceremony. For the Japanese, it's a symbol of national pride. But for the people of Awaji and Kobe, it was at last the safe crossing they have dreamed of for so long, linking the island with the mainland of Japan. Tourism and the vital link to hospitals and commerce is assured. For its creators, like director Makoto Kitagawa, it was a lifetime's work.
When the bridge was opened, I feel very happy. It was the happiest day in my life.
The 6-lane highway cuts the journey time from 40 minutes by ferry to less than 5 by car. 23,000 cars a day regularly use the bridge. But although it's designed to last for 200 years, looking after the bridge is an exacting 24/7 business. From the Bridge Control Center, they monitor every aspect of its operation. They use satellite technology to observe any movement of the mighty structure. The vital suspension system that supports the whole bridge has its own air conditioning system to stop the steel cable from corroding. Wind instruments measure the tiniest shift in the bridge's road deck. And since opening, the bridge has only closed 3 times in extreme weather. It's an extraordinary story, but the bridge's claim to be the world's longest may soon be challenged. Several continents away, the Italians are planning an even bigger bridge to link Sicily with the mainland. The Messina Bridge will be 3.3 kilometers long and carry a 6-lane highway plus a double-track railway line. But even the Messina Bridge may soon be surpassed. Emerging technologies could make possible suspension bridges spanning unthinkable distances. New carbon fiber cable will mean weight limits may no longer be a problem. Soon it could be possible to build bridges 10 times the size of the Akashi. 50-kilometer monsters could link England with France, Spain with Africa. But for now, the Akashi Kaikyo Bridge is the clear winner. The world's longest suspension bridge. 3 decades of planning, 10 years of construction, and $4.3 billion has made the impossible come true.